Have you ever pondered the significance of registers in a microprocessor? They're more critical than you might think. Today we're exploring the world within a microprocessor and the role registers play in it. But first, let's take a step back and understand what a microprocessor is. A microprocessor, often referred to as the heart of a computer, is an integrated circuit that processes instructions and controls other hardware in the system. Now, within this microprocessor, registers are like the brain's neurons. They are small, high-speed storage locations that store and manipulate data. Think of them as the microprocessor's short-term memory, storing vital information that the CPU needs for immediate use. They are crucial for the efficient and effective performance of a microprocessor. A prime example of this is the Intel 8086 microprocessor, a 16-bit microprocessor introduced back in 1978. This microprocessor is rich in registers, each serving a specific purpose. There are the general-purpose registers like the accumulator, base, count and data registers, which are used for a variety of tasks from arithmetic to data manipulation. Then we have the index and pointer registers, such as the source index and destination index, which are used for string operations. Furthermore, we have the segment registers, including the code, data, extra and stack segments, which point to specific segments within the microprocessor. Finally, there are the status and control registers, like the flags register, and the instruction pointer, which control the state of the processor and the execution of instructions. Each register in its own way contributes to the smooth and efficient functioning of the microprocessor. Without these registers, the microprocessor wouldn't be able to perform its tasks efficiently and effectively. So the next time you're using a computer, take a moment to appreciate these small but mighty components that make it all possible. Let's dive into the world of general-purpose registers. Our journey starts with the accumulator, also known as AX. This register is the workhorse of the 8086, handling arithmetic and data manipulation. But there's more to AX than meets the eye. It can split into two smaller 8-bit registers, AH the high byte and AL the low byte. This split personality allows for greater flexibility in handling data. Next up, we have the base register, or BX. This register often acts as a pointer to data in the data segment, making it a critical link between the CPU and the memory. Then there's the count register, CX. This register is like the metronome of the 8086, counting loops and string manipulations. Like the AX, the CX can also be divided into two 8-bit registers, CEH, the high byte, and CL, the low byte. This division allows the 8086 to multitask, handling multiple operations simultaneously. Finally, we have the data register, DX. This register is the go-to for input-output operations and is where the results of certain arithmetic instructions are held. And yes, you guessed it, it can also be split into two 8-bit registers, DH, the high byte, and DL, the low byte. This flexibility is a testament to the sophisticated design of the 8086. So there you have it, the general-purpose registers, AX, BX, CX, and DX. Each has its unique role, but they all share the ability to be divided into smaller registers, allowing for greater versatility and efficiency in data manipulation. These general-purpose registers form the backbone of the data manipulation capabilities of the 8086 microprocessor. They're like the chess pieces in a grand game, each with its unique movement and purpose, but all working together to achieve a common goal. Understanding these registers is key to understanding the power and potential of the 8086. So, now that we've explored the general-purpose registers, it's time to delve deeper into the 8086's architecture. But that's a story for another time. These general-purpose registers form the backbone of the data manipulation capabilities of the 8086 microprocessor. Next in line, we have the index and pointer registers. These registers are integral to the operation of the Intel 8086 microprocessor, and they play a central role in managing data flow within the CPU. Firstly, we have the source index or SI register. This register is primarily used as a source index for string operations. In simple terms, the SI register points to the location of the string or data set that is being read or manipulated. This allows the CPU to quickly and efficiently access the required data, improving the overall speed and performance of the processor. Next up is the destination index, abbreviated as DI. Similar to the SI register, the DI register is used as a destination index for string operations. Essentially, the DI register points to the location where the processed data or results of a string operation will be stored. By using the DI register, the CPU can swiftly store the results of its operations, further enhancing its performance. Now, let's talk about the base pointer or BP register. This register is used as a base pointer for stack operations. The BP register stores the base address of the stack, allowing the CPU to easily access the stack's data during operations. The stack is a special area of the computer's memory where temporary data is stored and retrieved in a last-in, first-out order, making it a crucial part of any CPU's operation. Finally, we have the stack pointer, also known as the SP register. This register points to the top of the stack. Just like the BP register, the SP register plays a crucial role in stack operations by allowing the CPU to keep track of the stack's topmost data. So, in a nutshell, the index and pointer registers, SI, DI, BP, and SP, are critical components of the Intel 8086 microprocessors architecture. They facilitate efficient data access and storage, contributing significantly to the CPU's overall performance. These index and pointer registers are key to managing data flow within the microprocessor. Now, let's turn our attention to the segment registers. Segment registers are another key part of the Intel 8086 architecture. These registers are responsible for pointing to different segments within the memory, including those containing the program code, data, and stack. Let's delve into each of these in detail. First up is the code segment or CS register. This register specifies the start of the memory segment where the program code is located. The CS register is automatically updated by the processor during far jumps, calls, and returns, ensuring the correct execution sequence of the program. Next, we have the data segment, or DS register. This points to the segment containing data. The DS register is used by most instructions when they reference memory. This allows the processor to access data stored in different memory segments. Thirdly, we have the extra segment, or ES register. Now, this one is a bit special. The ES register is typically used by certain string operations to point to an additional or extra data segment. This gives the processor the ability to work with more than one data segment at a time. And lastly, we have the stack segment, or SS register. The SS register points to the segment containing the stack. The stack, as you may know, is a data structure that stores temporary data and is essential for things like function calls and interrupt handling. The SS register ensures that the processor knows where the stack is located at all times. So in summary, each of these segment registers plays a vital role in the operation of the 8086 microprocessor. They ensure that the processor can access and manipulate data and code in different memory segments, allowing for efficient and flexible programming. Segment registers ensure the correct and efficient allocation of memory within the 8086 architecture. Finally, we arrive at the status and control registers. These registers have a unique role in the Intel 8086 microprocessor, acting as the command and control center of the entire system. Firstly, let's consider the flags register. This isn't just any ordinary register. It's a bit like a detective, keeping a close eye on the state of the processor after each operation. The flags register is home to individual bits that represent specific conditions within the processor. For instance, the 0 flag, or ZF, gets set if an operation results in 0. The carry flag, or CF, is set if an operation results in a value too large for the register. The sign flag, or SF, indicates whether the result of an operation is positive or negative, and there are many others. All of these flags work together to give us a detailed status report of the processor's state after each operation. Next, we have the IP register, also known as the instruction pointer. Think of the IP register as the microprocessor's tour guide. It always knows where to go next, pointing to the next instruction to be executed. This means that the processor always knows where to find its next task, ensuring a smooth and efficient operation. In essence, these status and control registers are like the brain of the Intel 8086 microprocessor. They monitor the state of the processor, guide its operations, and ensure that everything runs smoothly. Without these registers, the processor would be like a ship without a captain, aimlessly drifting in the sea of computations. So, in conclusion, the status and control registers play a pivotal role in the Intel 8086 microprocessor. They ensure that the processor can effectively carry out its operations and respond appropriately to different situations. The status and control registers are the microprocessor's command center, directing its operations and responses. We've covered a lot of ground today, exploring the intricate world of Intel 8086 registers. Let's quickly recap. The general-purpose registers, namely AX, BX, CX, and DX, are primarily used for arithmetic operations, data manipulation, and input-output operations. The index and pointer registers, including SI, DI, BP, and SP, play a crucial role in string and stack operations. Moving on, the segment registers comprising CS, DS, ES, and SS point to different segments of memory such as the code, data, and stack segments. Lastly, the status and control registers, flags, and IP represent the state of the processor and the location of the next instruction, respectively. These registers, each with its unique function, work together to make the Intel 8086 a powerful and efficient microprocessor. Understanding these registers is fundamental to grasping the inner workings of the Intel 8086 microprocessor, a landmark in computing history.